it does this really neat thing. It gets, say it's water 60 degrees. The volume of the water gets smaller and smaller and smaller and smaller. Now it's 40 degrees smaller, 30 degrees smaller, 20 degrees, 10 degrees smaller, okay? When it gets to like about 2 degrees, it kind of does something a little bit funny. And then when it freezes, it does a really weird thing. Unlike all other materials, it goes poof and it expands. It expands. Now, many people have theorized, and we think it's a pretty good theory, that if water didn't have this unique characteristic, there would be no life on planet Earth. Anybody know why? What's unique about water? What do you know about water freezing and ice? How does ice behave in water?
Ice will melt in water.
Huh?
Ice will melt in water.
It melts in water. What else does it do?
Turns it cold.
Yeah, there's the water cold.
What's the biggest piece of ice you know of?
Iceberg.
The iceberg.
An iceberg. What do you know about icebergs in the ocean?
Oh, they float.
They float. That's right. They float. Right? Now, if they didn't, why do they float? We haven't talked about density, but that's a hint. Density. Why do icebergs float on water?
Because
They have
more,
high density.
they have more water.
Because they have a lower density. They're lighter. The volume, the same volume of ice, okay, weighs less than the same volume of water. It has less density. So it floats as a result. Same reason a hot air balloon flies, okay? It floats. If it didn't float, what would happen? Did you know that when salt water freezes, okay, that almost all of the salt is squeezed out? What would happen is that the fresh water would freeze. If it didn't expand, it would sink. And why would that be a problem?
So because the people that live in Antarctica and the Arctic will not be able to live there.
Yeah, or there's this theory that basically all or almost all of the fresh water on Earth would be in the Arctic regions, the North Pole and the South Pole, and it would turn to ice, sink to the bottom of the oceans, and potentially stay there. And the Arctic regions would just become solid ice, and it would sink and stay there, right? So at any rate, there's neat characteristics about water, but water is the one exception to this rule about the particle model of matter, okay? It gets smaller just like everything else as it cools down, but then as it freezes, poof, it gets bigger. Yeah, it's totally unique in that way. Now I can see you're yawning. So normally I wouldn't lecture this long, but this is your executive summary for this chapter. Look here. How can we prove that let's just flip through this, okay? How can we prove that particles are always vibrating? Turn to the next page, 6.2. What does that say?
Diffusion.
Diffusion. You can see it from there, right? You can see it from there. It's the only thing you can read from a distance. Diffusion. Think I'm going to ask you a question about diffusion?
Yeah.
You better believe it. I'm going to ask you a question about diffusion. You must know what diffusion is. Do you know what diffusion is, So Young? No? All right. Now, diffusion is how things spread out, is how they mix. All right? You definitely need to know about this. Explaining diffusion. There's a neat thing. I'm going to do this later, okay? See this test tube with water in it? See this test tube with water right up there? I'm going to very carefully take an eyedropper of dye, yeah, and I'm going to, or food coloring, I'm going to put it in the bottom of the test tube and squeeze it out. And it will stay in the bottom. Why will it stay in the bottom?
Because the density is way higher.
Because the density is higher than water, so it will sink in the water. Now, the reason I have it up there is so that it won't get shaken or moved. In a matter of weeks, the whole test tube will be, say I put red food coloring in there. The whole thing will be red. Kenapa? How will that happen? If I don't stir it, why will that happen?
Because once it makes the
Particles move
particles
around
will,
by itself.
particles move around, like spread farther and farther.
That's right. The particles are always vibrating and they bump off of each other and they will move the food coloring themselves. Okay? They will move the food coloring themselves. And we'll watch that happen. Tomorrow you'll come in and you'll see it. It'll be a little bit mixed, and then it'll be a little bit more mixed, and a little bit more mixed. You can do the same thing. Here's a simple extra credit project you can do. Take some sugar, put it in a glass at home, put some water in it. Don't stir it. Take a picture of it every day for a week. See what happens to the sugar. You will see it might take more than a week. It will disappear without you stirring it. What happened to the sugar? It dissolved in the water. Why did it dissolve without stirring it?
Sweet,
Why did it dissolve without stirring it?
because the molecules bumping into each other, so they chip off part of the sugar.
That's right. This guy got it. You got it?
Is it still sweet anyways?
Yeah.
Yeah, then it'll be sugar water, right? So you could mix your sugar into your tea that way. It just takes a week. A way to speed it up is stir it. Another way, have you ever noticed this? Is it easier to mix sugar in iced tea or hot tea?
Hot tea.
Hot tea, why? Based on the particle model of matter.
We're not asking what do you
Because
like.
because the particles, when they're hot, they're moving a lot more,
So they
and
bump faster.
they will dissolve the sugar more quickly.
When they bump
right?
faster, the sugar.
Now, I usually don't lecture this long. Sorry about this, but we're just going to keep going for it. Using diffusion, that's one way to prove it. There's this neat guy. They're talking about what I just told you right here. Look at the pictures. Investigating diffusion. We're going to do some of these experiments. Hey, look, there's the one that I just told you about, but it's with different temperatures. Okay, now here's a neat guy. This guy, his name is Mr. Brown. There's something called Brownian motion. Brownian motion. Have you ever been in a house and seen the sunlight? It has to be no air conditioning, nothing moving. Yeah, not much air moving. And see sunlight coming through the windows, direct sunlight. And if you're looking carefully, you can see dust floating in the air.
Yes.
Yeah? Now, if you look at one piece of dust very carefully, you'll notice, occasionally you can see this, that piece of dust, instead of just like falling or floating, moving in one direction, it will all of a sudden go, doop, doop.
Go back.
It'll move in random directions. Why is it moving in random directions?
Because the particles are
Somebody other than Kenneth.
The gas. The gas particles.
The gas particles what?
Bump each other.
They're bumping into each other, right? And it might run into some O2, a molecule of oxygen, and they might push it and it goes in a different direction. Mr. Brown saw this and witnessed this, and I was going to try to show you this today, but something happened to our microscope that I can put on a TV. It might be fixed soon. He witnessed this with pollen grains under a microscope, and he saw them moving in a random way. Well, these things are not alive. They're not alive, but they're moving. Why would they be moving? Same reason, particles bumping into them. Okay? And then, we talked, remember we did this with the syringes? We took a syringe and you tried to compress gas. Can you compress gas?
Yep.
Yes. Can you compress water? No, we tried that, right? Here's a picture of a syringe. Somebody compresses it. All of a sudden it gets harder to compress. Why is it getting harder?
The particles still move.
Because the particles are trying to push off of each other and stay away from each other, but you're forcing them to get closer, but they don't want to. So when I compress this, right, if I let it go, it goes back up. Right? Right in your book. Learn from the pictures, people. Learn from the pictures. And then finally, here's the last chapter. It talks about why does a balloon float up. And we're even going to briefly look at this chapter, okay, which deals with, oh wait, is this atoms?
Yep.
Yeah, atoms. Now there's one guy I mentioned to you already, very important guy, at least to me, because somehow we're family. There's a guy up there on the periodic table. His name is Ernest Rutherford.
Is your family?
Yeah. Ernest. He studied science earnestly. He was a good and famous scientist. He had, one thing that you should know is that theories, and this is all the Cambridge stuff that you need to know for this Cambridge checkpoint exam. Okay, I'm giving you the summary right now. Before you take that exam, I'm going to put this video up. You should watch it if you can hear it well, because it's what you need to know. Ernest discovered, well, there were many theories about atoms, yeah? At one point we thought there was this idea of an atom, and we thought that they were just particles, maybe like the marbles, just little chunks, solid bits of matter. And then we started discovering different things about them, and different people had different ideas about them. And then finally, you get to Ernest Rutherford, right? And I think this is in your book. It might be in the 9th grade book. Ernest had this neat thing, yeah? He, like Einstein, had this characteristic. You know what Einstein said was the most powerful human characteristic? And I worry about this with you guys. Some of you are a bit ADD. You know what that stands for? Attention deficit disorder. I don't know if it's really a disorder. It means you have a hard time to focus your mind. Einstein said the most powerful human strength is our ability to focus our mind on one thing, on a topic, for an extended period of time. That doesn't mean 5 minutes, 10 minutes, even an hour. It means like days, years. Einstein kept on asking, his famous story, he kept on asking, God, what were you doing when you made light? Yeah? What were you doing when you made the universe? And then finally, he basically had a vision in the middle of the night, and he had some idea about it. This guy, Ernest Rutherford, had the same thing. What's going on with particles and atoms, right? Arthur, sorry, I'm putting you to sleep, buddy. I know, I don't usually lecture like this, but it's like a bedtime story. So Mr. Rutherford was going to bed one night, and he was asking, what's going on with atoms? And then he woke up in the middle of the night, and it's kind of a famous story. He had this vision that atoms were just like solar systems. What are solar systems like? There's a little sun in the middle, and there's planets orbiting around. And we'll study the solar system before the end of this term, God willing, we get there. The solar system and space itself is made up of 99.99999% nothing. And so he had this vision, and he literally, they say that he told this story that when he wanted to get out of bed in the morning, and he was afraid because he had discovered this, that he would step through the floor and into a different dimension. Because he realized that atoms were made up of almost nothing, just all empty space. It turns out he was right. And then he's famous for several other reasons, right? But check this out. Have you ever heard of the Big Bang Theory?
Yes.
You guys know about the Big Bang? The idea was that all the matter in the universe...
Is it a TV show?
No, it's
Yeah, I think there might be a TV show too. Yeah. But all of the material in the universe was gathered in one place. And then it exploded. It exploded.